So my name is Brittany Cox, and my topic is how to calculate equilibrium concentrations of reactants and products given the equilibrium concentrations of some other reactants and products. So I'm going to reference my notes. I'm not going to be able to remember all of this off the top of my head, so if I look down, that's what I'm doing. So when you get these problems, the first thing you want to do, I think the first thing you should always do for every problem ever we've learned at this point, is to start by writing the balanced chemical equation. And in the equilibrium problems, that's going to have the double-sided arrow going each way. Since we're establishing an equilibrium, it's not just a finished reaction going in one direction. So you write the balanced chemical equation, and the next step is to write the ICE table directly below that equation. So I for initial concentration on one line, C for the change in the next line, and E for equilibrium on the third line. And so after you do that, you look at the problem to see what concentrations that you've been given and fill those in the I row for for the initial. So say you have, sodium chloride, and it tells you that the initial concentration is 0.5 molar. You would write that underneath sodium chloride in the initial row. And if you don't have any quantity for a reactant or a product, that means that the reaction is going to proceed in that direction to make some of it. And so I always just fill in a 0 because I like to know. I just like to have everything filled in, whether there's initial concentration or nothing. I want to see that. Okay. Same value x. So after you do that, you finish the initial row and you go down to the change, and anything that has a 0 is going to have something added on to it. And anything that already has an initial concentration is going to have some value subtracted from it so that it can, proceed to make the other products or reactants that don't have a concentration yet. And if one of the things to remember that can get tricky is if there's ever a coefficient in front of any of the reactants or products, when you're doing the change row of the ICE table, you have to remember to include that coefficient. So let's say you're starting with 2 moles of sodium chloride, and that's going to make some other products. So it's not just going to be a minus x from that, minus a value. It's going to be the x multiplied by the coefficient. So it will be a minus 2x. Same as if something on the product side that has no initial concentration, if there's a coefficient 2 in front of that one, then it's going to be a change of increased 2x. So whatever the coefficient is in front of the reactant or product, that also goes in front of the x in the change row. So if there's no coefficient, you assume it's a 1, which means it would just be a minus or plus in x with no written out coefficient. All right, and then in the third row of the ICE table, which is equilibrium, you just take whatever number is in the initial row, add or subtract the value and change, and that's going to be your equilibrium concentration for each product or reactant. So once you have the ICE table all set up, you have to set up your KEQ expression, which is just the K at equilibrium, since that's what we're looking for. So you set that up, remembering that KEQ is equal to the concentration of all the products multiplied by each other over all the concentrations of reactants multiplied by each other. All right, and so you should have the KEQ value. Either it's given to us in the equation, or there's a table, somewhere like in the quiz or homework that we're doing, whatever, that has it that you can look it up. So you take that value and you set it equal to the concentration of all products on the top multiplied by each other over the concentration of all of the reactants multiplied by each other in the denominator. And so, like I mentioned earlier, you got to make sure that any coefficients that you have stay in front of the x when you're writing out the KEQ expression, but also that if there's any coefficient other than 1, that expression is raised to that power. So if the change is 2x in the KEQ expression, it's going to look like 2x in parentheses squared. If the change is 4x, it'll be 4x in parentheses to the 4th. So whatever the number is in front of the coefficient, it's also raised to that power in the KEQ expression. Okay, so now that you have your KEQ expression written out, before solving and multiplying everything out and potentially having this annoying quadratic that you have to use a quadratic equation to solve for, or using a quadratic solver or whatever, check to see if you can simplify. And the way you do that is if the k value that you're given is at least 1,000 times smaller than all the concentrations that you're given in the problem, then you can safely simplify, making the solving of the KEQ expression a lot easier. So how I do that is I take the KEQ expression, multiply it by 1,000, and I compare that to all of the concentrations that were initially given. If 1,000 times the KEQ is less than all those expressions, then you can safely simplify by crossing out just the different, like minus x in the numerator and or the denominator of the KEQ expression. So whether or not you simplify, whatever you have left, you multiply out to solve for x. And once you have x, that's great, but you're not quite done. You have to go back up to your ICE table and plug that into the E row, so E standing for equilibrium, to find the concentration of all your different products and reactants. So going back to the example I think I said earlier, if your initial concentration is 0.5 molar of sodium chloride, the change would be 0.5 minus x, and to find the equilibrium concentration, you would take 0.5 minus the value you find for x, and then that is your equilibrium concentration of that particular product. And you do that for all of the products and the reactants in order to find the equilibrium concentrations of all of your products and reactants. I think that is it. Hopefully this helps you understand the concept a little better, or clarifies it a little. All right, that's it. Thank you.